let's wait for 5 minutes so that people can join. So this is our last tutorial session for this course. Today we'll be discussing some problems related to compact operators and their spectrum. So let's start with true false. State whether the following are true or false. Question number one. Let H be a Hilbert space. And P be a bounded linear operator defined on H. P an orthogonal projection. They are saying that the only eigenvalues of P are -1, 0, and 1. So let's see what eigenvalues, what does an orthogonal projection, what eigenvalues does an orthogonal projection has? Solution, and see whether the given statement is true or false. So for an orthogonal projection, we know that P is equal to P star is equal to P square. This is a well-known fact. We have proved it earlier also. We know that for an orthogonal projection, P is equal to P square, which is equal to P star. This implies obviously P is self-adjoint. P is equal to P star. And for self-adjoint operators, we know that all eigenvalues are real. Its eigenvalues are real. Also, the given set of possibilities is also a subset of real numbers, so that's not an issue. Now, suppose lambda be an eigenvalue. Let lambda belonging to R be an eigenvalue of P. This implies there exists some non-zero vector x in H, the space defined on H, such that this is the definition of eigenvalue. Px is equal to lambda x. Now using this one, we will get this implies lambda x, which is equal to px. Now since p is equal to p square, I can replace it by p square, which is p of px. And again, since lambda is eigenvalue corresponding to the vector x, eigenvector x, so this is lambda x. Now since p is linear, this lambda will come outside, p lambda times px. And again, since px is equal to lambda x, this is lambda square px. Therefore, we get lambda x is equal to, sorry, this is x square x, lambda square x. Let's mark this as 2. And this implies lambda times lambda minus 1 x is equal to 0. Now, since x is a non-zero vector, this implies either lambda is equal to 0 or lambda is equal to 1. Clearly, lambda equals to -1 is not a possibility, because if we had lambda equals to -1, then by equation second, we would have got minus x is equal to x, which would imply that x is equal to 0, but eigenvectors are non-zero vectors. So therefore, therefore the possibility for eigenvalue are 0 or 0 and 1 only. This -1, p cannot have -1 as its eigenvalue. Therefore, the given statement is false. Lambda equal to -1 is never a possibility. The given statement is I hope this solution is fine. Let's go through it again. If you have any doubt, you can ask. Okay, then let's move to next question. Question number 2. Let H be a Hilbert space. If S is a bounded linear operator defined on H is such that S square is equal to identity and it is self-adjoint, S star is equal to S, then S can be written as I minus 2 times P, where P belonging to the space of bounded linear operators on H is some orthogonal projection, is an orthogonal projection. They're saying that if S is such that S square is identity and it is a self-adjoint operator, then we can find an orthogonal projection P such that S is equal to I minus 2P. So let's see. If I define some function P such that it is S minus I by 2, so eventually S will be I minus 2P, and prove that it will be an orthogonal projection. In that case, directly I'll be done. In that case, the given statement would be true. And if that P is not orthogonal projection, then the given statement is false. Now consider P from H to H. P of X is equal to 1 by 2 I minus S X for every X in H. Clearly, since I and S are bounded linear operators, this P is also a bounded linear operator. P belongs to LH. Now, we will show that it is an orthogonal projection as well. Now, P star. P star is nothing but 1 by 2. From here, we can see that P is equal to 1 by 2 I minus S. So, P star would be I minus S star, which is we know is equal to since identity is self-adjoint, I minus S star. Now again, since S is also self-adjoint, so this is I minus S again, which is equal to P. Therefore, P star is equal to P, and for any X in H, P square X is equal to 1 by 4 times I minus S square at X, which is 1 by 4. This is nothing but basic calculation. S square, basic algebra, minus 2S at X. And since S square is equal to identity, so this 2 will come outside and get cancelled out. This is 1 minus S X, which is Px. Therefore, P square is equal to P. Let's mark this as first and this one as second. Using first and second and the characterization of orthogonal projection, we know that P from H to W is an orthogonal projection if this inner product PXY is equal to XY for every Y in W, if and only if P is an orthogonal projection onto W. We will be using this characterization in order to show that this P is an orthogonal projection. Now let W be the range space of P. Obviously, this is a subspace space of H. Now, for any X in H and Y in W, Pxy, this is equal to X P star Y by characterization of adjoint. This is equal to, now since we have seen that P star is equal to P, this is equal to X Py. This is by equation first, which is equal to X Y, because for every Y in W, Y is equal to PZ, because W is range P, range of P. This is equal to PZ for some Z in H. This implies Py is equal to P of PZ, which is P square Z. And since P square is equal to P, this is equal to PZ, and which is equal to Y. Therefore, Py is equal to Y. So this implies Pxy is equal to Xy for every Y in W, which is range of P, and X in H. Therefore, P is an orthogonal projection. Obviously, this P belongs to the space of bounded linear operator on H, and since P is equal to 1 by 2I minus S, this implies S is equal to I plus 2P. 2P. This is I minus 2P. No? I minus 2P. Therefore, the given statement is true. I hope this solution is fine. Please go through it once again, and if you have any doubt, please let me know. Mainly, we have you firstly defined P in such a way that P S is equal to I minus 2P, and then tried to prove that this P will be an orthogonal projection. For that, we have shown that it's P square is equal to P and it is self-adjoint. Using these two facts, we and the characterization of orthogonal projection, we have shown that this P is actually an orthogonal projection and S is equal to I minus 2P. Okay, if there's no doubt, we can move forward. Question number 3. Let V be the space of all continuous functions defined on closed interval 0 to 1. And A be a bounded linear operator on V, be defined as follows: A from V to V. A at AF is a vector in V. That means AF is a continuous function defined on closed interval 0 to 1 in such a way AF at any point t is equal to t times ft for every t in 0 to 1. And this is how we define A for every f in V. Then they are saying that this operator A is compact. Operator A, sorry, operator A is compact. We know that a compact operator maps bounded set to compact set. That means if A B01, where B01 is closed unit ball in the domain, is compact in the range, compact in V, then we say that A is a compact operator. So let's see whether this is compact or not. Then now suppose A is compact and we have a bounded sequence. If we have a bounded sequence Fn in V, then AFN must have a convergent subsequence because because range, sorry, if we have a bounded set B, then A of B, this is compact in V, in the codomain. And since it is compact, it must have a convergent subsequence. So this any sequence over there must have a convergent subsequence. Must have a convergent subsequence. So we will see. We will try to we'll be proving using contradiction that A is not compact. That means we'll search for a sequence Fn which is bounded in V, but AFN can never have a convergent subsequence. So for that, let's consider the sequence Fn in C01. Fn t is equal to t to the power n for every n and n and t in closed interval 0 to 1. This implies AFN at any point t is equal to t times t to the power n, which is t to the power n plus 1, which is basically Fn plus 1t. This implies the sequence AFN is nothing but Fn plus 1, or we can write it the sequence Fn also. This is for n1 to infinity, and this will be from n from 2 to infinity. Okay. Here, norm Fn, infinity norm, this is supremum mod Fn t belonging to 0 to 1. We know that for t belonging to closed interval 0 to 1, Fn t to the power n will also belong to the closed interval 0 to 1, so that its supremum will be 1. This implies Fn is a bounded sequence in C01. Now, if A is compact, then there exists a subsequence Fnk such that AFnk is convergent. Now, since Fnk is nothing but Fnk plus 1, this implies AFnk plus 1, sorry, not A, this is Fnk plus 1 is convergent in V, which is C01, is convergent in V, which is C01. Now, if you look at the sequence Fnk, Fn, let's see Fn, this Fn is t to the power n. So for n equals to 1, this is straight line fx equals to t. Then we have ft equals to t square, ft is equal to t cube, and so on. So we know that pointwise, this fnt converges to ft, which is 0 for t not equal to 1, and it is equal to 1 for t equal to 1, as n tends to infinity for every t in closed interval 0 to 1. So this is the pointwise limit. Now they're saying that Fnk is convergent in C01. That means Fnk plus 1 is convergent, is uniformly convergent, because the convergence in C01 is the uniform convergence. Fnk plus 1 is uniformly convergent, convergent, and this is a uniformly convergent sequence of continuous functions. And we know that uniformly convergent, the uniform limit of, like, whenever a sequence of continuous function converges uniformly, then the limit must be continuous as well. So that means, now, since uh, Fnk plus 1 converges uniformly, and Fnk plus 1 is a sequence of continuous functions, then the uniform limit of the continuous functions is also continuous, is a sequence of continuous functions. This implies F, because obviously uniform limit should also be pointwise limit as well, and by continuity, by uniqueness, this pointwise, the uniform limit should be equal to this pointwise limit. So this implies F must be continuous, which is a contradiction. Hence, by contradiction, the given statement is so basically we have constructed a sequence in the domain which is bounded such that its image cannot have a convergent subsequence. So if an operator is compact, it maps bounded sequence to compact sequence. That means the image must have a convergent subsequence. But here we are getting a contradiction, since this sequence fnt defined to be fnt equals to t to the power n, its image is basically the same sequence itself. And if if it had a convergent subsequence in C01, then that would have given us uniform convergence. And we know that uniform limit of continuous functions, of a sequence of continuous functions, is always continuous. That would have given us that this function f is continuous, which is a contradiction. Hence, the given statement is false. I hope this solution is fine. If you have any doubt, you can ask. Therefore, this operator is not compact. Okay, if there is no doubt, we can move to next problem. Next, we will look at eigenvalues of uh, above defined operator, the operator that we have been discussing in question number 3. Oh, let V and A be as in question number 3. Then A has no eigenvalue. Let us see whether this operator has any eigenvalue or not. Solution. Now let if possible, lambda be some eigenvalue of A. Suppose lambda be an eigenvalue of A. This implies there exists some function f which is not trivially 0 in C01, continuous function defined on closed interval 0 to 1, such that AFT is equal to lambda ft for every t in close 0 to 1. And the way AFT is defined, t times ft is equal to lambda ft. T minus lambda ft is equal to 0 for every t in 0 to 1. Now, if this lambda does not belong to closed interval 0 to 1, this implies t minus lambda is never 0. That means ft should be equal to 0 for every t in closed interval 0 to 1. This implies f is trivially 0, which is Not the case because we have taken this, because f is an eigenvector basically, so eigenvectors are non-zero vectors. Now this implies this lambda belongs to closed interval 0 to 1. Or we can say that lambda is equal to T naught for some T naught in closed interval 0 to 1. So this implies we have T minus T naught Ft is equal to 0 for every t belonging to closed interval 0 to 1. Now this term is 0 for t equals to t naught, else this is non-zero. Therefore, ft must be 0 for every t belonging to closed interval 0 to 1 minus t naught. At t naught, it need not be 0, but at rest of the points, it must be 0, and so that this product is 0. Now, since f is continuous and it is 0 everywhere in the closed interval 0 to 1 except at one point t naught, that would eventually give us that f should be equal to 0 at t naught as well by continuity. By continuity of f, we must have f at t naught equals to 0 as well. Now, this implies that again f is a trivial function, trivially zero function, which is not possible because again f is an eigenvector. So therefore, it cannot have, because we are getting contradiction in either of the cases, therefore it cannot have any eigenvalue. Therefore, A does not have any eigenvalue. Therefore, the given statement is true. I hope this solution is fine. If you have any doubt, you can ask. Please go through the solution once again. Oh, I'm so sorry. I was muted. Uh, yeah, let me record it once again. So we are given that H is an infinite dimensional Hilbert space and A is a compact bounded linear operator defined on H. If they are saying that if A has closed range, then A should have finite rank. Now let's start with let's denote Ra to be the range of A, and since Ra is a closed subspace of the Hilbert space H, Ra must be Hilbert space in itself because it is a closed subspace of a Hilbert space. And clearly, if we define A from H to range of A, then obviously this is a onto compact bounded linear operator. Now, since H is a Hilbert space and null space of A being the inverse image of singleton 0 is closed subspace of H, it can be complemented. That means H can be written as Na plus Na direct sum with orthogonal projection of Na. And we know that if eh, if kernel of the domain kernel of an operator can be complemented, in that case we can find its right inverse. So let's that right inverse can be given by if we define some function operator some bounded linear operator S from Ra to H such that Sy is equal to X. So we don't know whether this is a bounded linear operator or not. We'll start with just defining S from Ra. Ra is again a Hilbert space to H, where Sy is equal to X, where this Xy is an element in the orthogonal projection of the kernel of A such that Ax is equal to Y. So the first thing that we should check is that whether this function S is well defined or not. The problem will occur when some element Y in range space of in Ra will have two images. That will be the point of ambiguity. Now, suppose if there exists some x1 and x2 such that ax1 is also equal to y and ax2 is also equal to y. In that case, sy will may not be defined. So, in this case, we will get a x1 minus x2 is equal to 0. That means x1 minus x2 belongs to null space of A. Also, for any n belonging to null space of A, the inner product x1 minus x2 with n is equal to x1 with n minus x2 with n. Since x1 and x2 are elements in Na perp, these, these inner products are 0. This implies, and this is happening for every n and Na. That means x1 minus x2 belongs to orthogonal projection of Na. That means x1 minus x2 belongs to intersection of Na and its orthogonal projection. That means x1 minus x2 is equal to 0 or x1 is equal to x2. Hence, this function is well defined. You can also see that this is in fact a bounded linear operator, continuous linear transformation. Yeah, again, bounded linear operator using the open mapping theorem. Using the Since A is an onto bounded linear operator, we can use the open mapping theorem and the linearity of A to show that this S is actually a bounded linear operator using the open mapping theorem and linearity of A. We can see that this S belongs to L R A to H. That means S is a bounded linear operator. So what we needed to show, what we were main concern was we need to show that, see that if A has a, sorry, if rank of A is finite or not. So in order to show that rank of A is finite or not, we will look at a sequence in closed unit ball, because we know that in any Hilbert space, or in a Hilbert space, uh, in a Hilbert's yeah, since we are working on a Hilbert space, let's not worry about other things. Or in a Hilbert space, we know, no, this now see, the rank, sorry, the range of A is a subspace of H. Now this is a yeah, again this is also a Hilbert space. Okay, okay, that's fine. So in a Hilbert space, we know that it is finite dimensional if and only if its closed unit ball is compact. We know that, so we will be using this fact in order to see that it is finite dimensional or not. If we get that closed unit ball in range space of A, in range A, is compact, then we will directly get that the range space is finite dimension. Yes, let's do it once again. Yeah. So now let Yn be a sequence in closed unit ball of Ra. So Yn is a sequence in closed unit ball. If it has a convergent subsequence, Yn being an arbitrary sequence, we will get that closed unit ball is compact in Ra, and hence Ra is finite dimensional. Now since Yn is bound, therefore Yn is a bounded sequence. Obviously, since it belongs to closed unit ball, its norm is less than or equal to 1. Yn is a bounded sequence in Ra. Now, since S is a bounded linear operator defined on Ra, this implies Syn is bounded sequence in the range of S, which is a subset of H. Syn is bounded sequence in H. And how Syn is defined? Syn is Xn is bounded sequence in H, where Xn is such that Yn is equal to Axn. That means that is the sequence where Yn is equal to A. So now Xn is a bounded sequence, and Xn is a bounded sequence and A is compact. Now since A is a compact operator, there exists a subsequence Xnk of the sequence Xn such that this Axnk is convergent in the range space of A. That means the sequence Ynk, because that is how Xn is defined, is convergent in range of A. Now we started with an arbitrary sequence in closed unit ball of range A. We proved that it has a convergent subsequence. That means the closed unit ball in range in Ra is compact, since Yn is an arbitrary sequence in closed unit ball of Ra. This implies closed unit ball B01 is compact in RA. And we know that this happens if and only if RA is finite dimensional. That means the range space of A is finite dimensional. That means the rank of A is finite. This implies, because rank of A is nothing but the dimension of range space of A. Rank A is finite, or A has finite rank. Therefore, the given statement is true. I hope this solution is fine. Mainly, firstly, we have uh, shown that since H is a Hilbert space, the null space of A is can be complemented, and hence we get a right inverse, which is and this right inverse must be uh, right inverse is a bounded linear operator. Using this, we have shown that an arbitrary sequence in closed unit ball of range of A must have a convergent subsequence, and this that means the closed unit ball is compact. And we know that a closed unit ball is compact in a Hilbert space if and only if it is finite dimensional. Hence, A has finite rank. I hope this solution is fine. If you have any doubt, please ask. Okay, so if there is no doubt, we can move forward. Number 6. Uh, the operator A defined, the bounded linear operator defined on L2 defined as follows. A x is equal to 2 by 9 x1 by 16 x2 4 by 25 x3 and so on for every x equals to x1, x2, so on, and L2 is compact. So let's see whether this operator is compact or not. We will show that this operator is indeed compact using the fact that it can be made as limit of a sequence of compact operators. We all know that if we have a sequence of compact operators and it converges to some operator in the space of bounded linear operators, that means with the operator norm, it converges to some operator A, then that must also be compact. That is, the space of compact operators is closed. So using this fact, we will show that this A is indeed compact. Now consider the sequence of operators AN from L2 to L2. ANX is equal to, we will be taking the first n terms as that in A. So the nth term would be n plus 1 by n plus 2 square xn, and after that this is 0. This implies clearly rank of AN is n, which is finite for every n, and norm ANX L2 norm square, this is equal to summation k from 1 to n, because rest of the terms are 0, n plus 1 by n plus 2 square xn square. Now since n plus 1 by n plus 2 whole square is less than equal to 1, this is less than equal to summation k from 1 to n xn square. Since n plus 1 by n plus 2 square is less than equal, sorry, this is k. So yeah, let me write it again. So this is k plus 1 by k plus 2 square xk. This is xk square. Since k plus 1 by k plus 2 square, this is less than equal to 1. And this is obviously less than equal to L2 norm x square. Therefore, AN is finite rank operator, finite rank bounded linear operator. And we know that finite rank bounded linear operators are compact. Therefore, AN is finite rank bounded linear operator for every n in n. Hence, AN is compact for every n in n. Now we claim that the sequence AN minus A converges to 0 in, or we should write AN converges to A in L2. That means norm AN minus A converges to 0 as n tends to infinity, and this norm is the operator. Now, for any x belonging to L2 minus 0, that means it's a non-zero vector in L2, this AN minus A x L2 norm square by x L2 norm. This is equal to, now an minus a, since first n terms of an and a of x and an of x are same, so we would be left with the terms after n plus 1. So this is 0, 0, so on, 0, and next term would be n plus 1. So this is n plus 2 by n plus 3 square xn, and so on, L2 norm square by, yeah, this is summation k from 1 to infinity mod xk square. This is summation k from n plus 1 to infinity k plus 1 by k plus 2 square xk square by summation k from 1 to infinity mod xk square. Now this is this is less than equal to summation k from n plus 1 to infinity k plus 1 by k plus 2 square square. That's because xk square is always lesser than equal to norm x square, and that can be taken outside, and it will be cancelled out by the denominator norm x, denominator L2 norm x. So eventually we'll be left with this term only. Yeah, which is which tends to 0 as n tends to infinity, because it is tail of a convergent sequence, since summation k from 1 to infinity k plus 1 square by k plus 2 power 4 is a convergent series, and hence its tail term will converge to 0. In fact, let's keep it this much only for the time being. Now this happens for every x belonging to L2 minus 0. Therefore, now since the right hand side is independent of x, we can take supremum. Supremum x belonging to L2 minus singleton 0, norm an minus a x 2 square by x2. This is less than equal to summation k from n plus 1 to infinity k plus 1 by k plus 2 square cos square whole to the power 1 by 2. Now this will tend to 0 as n tends to infinity, because again this is a tail of a convergent series. Summation k from 1 to infinity k plus 1 square by k plus 2 power 4. So this is basically kind of a p series, and eventually this is something similar to 1 by summation 1 by k square, which is finite, or we can write is a convergent series, and hence its tail converges to 0. And the left hand side is actually norm, the operator norm an minus a goes to 0 as n tends to infinity. Therefore, this a is a limit of compact operators, and since this space of compact operators is closed, therefore a must be compact. This implies A is limit is okay. Therefore, an converges to A in the space of compact operators, which is closed. Therefore, A is compact. Hence, the given statement is true. An belongs to and An is compact for every n and n. Therefore, A is compact. Yeah. Hence, in this is a very nice trick. We generally use this method to show that some operator is compact if we show that it is a limit of a sequence of finite rank operators. We all know that finite rank operators, finite rank bounded linear operators are compact. Therefore, if we can show that our given operator is limit in the operator norm of a sequence of finite rank operators, then eventually it turns out to be compact operator. I hope this solution is fine. If you have any doubt, you can ask. So if there is no doubt, we can move forward. Next, we have answer the following type problems. Question number 7. Let V be the space of continuous functions defined on closed interval 0 to 1, and A belongs to the space of bounded linear operators on V, be defined by A F T is equal to T times F T for every T in closed interval 0 to 1, and F in V computes the spectrum of A. First, let's recall the spectrum of A is the space of all those scalars lambda such that A minus lambda I is not invertible. Explanation. Suppose lambda be a scalar such that it does not belong to closed interval 0 to 1. Let lambda does not belong to closed interval 0 to 1. In this case, we claim that A minus lambda I is bijective, and hence by open mapping theorem, it is invertible. Therefore, lambda cannot be in its spectrum. That would give us that our spectrum should be subset of closed interval 0 to 1. So our main aim is to show that A minus lambda I is bijective if lambda is not in closed interval 0 to 1. So firstly, let's start with injective. Let X belongs to kernel space of A minus lambda I. This implies A minus lambda I X is equal to 0. Sorry. Since we are in C01, let's take this to be F. So that means this is equal to 0 for every t in closed interval 0 to 1. That means TFT minus lambda FT is equal to 0 for every t in closed interval 0 to 1. Since lambda does not belong to 0 to 1, this implies lambda is not equal to t for every t in closed interval 0 to 1. This implies our ft should be equal to 0 in order to make this product equal to 0 for every t in closed interval 0 to 1. That means f is trivially 0. This implies kernel of A minus lambda I is singleton 0. This implies A minus lambda I is injective. Moreover, for any G in V, C01, taking Ft to be equal to Gt by lambda minus t for every t belonging to closed interval 0 to 1. Since lambda is not equal to lambda is not in closed interval 0 to 1, this Ft is well defined. Moreover, it is continuous because G is also continuous. This implies F belongs to C01 and A minus lambda I. A minus lambda I Fp. So I did this. I should take T minus lambda. No? So this should be T minus lambda. This is AFT is TFT. So this is T minus lambda. Ft is Gt by T minus lambda, which is equal to Gt. This implies A minus lambda I F is equal to G. Since G belonging to V was arbitrary, therefore A minus lambda I is surjective as well. Hence bijective because it was injective earlier. Therefore, our spectrum is a subset of closed interval 0, 1. Obviously, it cannot contain any element which is not in closed interval 0 to 1. Implies A minus lambda I is invertible by using open mapping theorem and bijectiveness. Now, for any lambda belonging to closed interval 0 to 1, this A minus lambda I cannot be onto. It cannot be invertible. So proceeding as above. Now, for any lambda belonging to closed interval 0 to 1, suppose A minus lambda I is invertible, implies A minus lambda I is surjective, implies for every G in V, there exists F in V such that A minus lambda I F is equal to G. And this is equal to T minus lambda Ft is equal to Gt, implies Ft is equal to Gt by T minus lambda belongs to V because F is in V, which is C01. But since lambda is equal to some T naught, therefore this F will fail to be continuous at that T naught, which will give us a contradiction. But since lambda is equal to T naught for some T naught belonging to closed interval 0 to 1, F fails to be continuous at T naught. This implies F does not belong to C01, which is RV, which gives us a contradiction. Therefore, A minus lambda I is not invertible for every lambda belonging to closed interval 0 to 1. This implies our spectrum is exactly equal to closed 0, 1. A is equal to close interval 0 to 1. Therefore, yeah, we got the spectrum of this operator. I hope this solution is fine. If you have any doubt, you can ask. So if there is no doubt, we can move forward. Number 8. Let Aij, ij from 1 to infinity be a double sequence. That means it's depending on I and j. be a double sequence such that the series summation I j from 1 to infinity aij square is finite. So the sum is actually 2 times sum j from 1 to infinity aij square. This is finite. For any x in L2, x equal to x1, x2, and so on belonging to L2, we define an operator A such that the ith element of AX is equal to summation j from 1 to infinity aij xj. That means this AX is a sequence of the form. Its first term is summation j from 1 to infinity a1j xj, j from 1 to infinity a2j xj, and so on. So that this A, so that this A is a bounded linear operator on L2, and moreover it is compact. Again, as done earlier, we will show that it is a limit uh, limit of a sequence of compact operators, mainly the finite rank operators, in order to show that this is compact. Solution. Clearly, this is linear. All we need to show is the continuity. For that, for any x in L2, we can see that the L2 norm of x square, this is nothing but summation j from 1 to infinity a1j xj, summation j from 1 to infinity a2j xj, and so on. It's L2 norm. So this is summation I from 1 to infinity mod summation j from 1 to infinity aij xj square. This is less than equal to summation I from 1 to infinity j from 1 to infinity aij square times summation j from 1 to infinity mod xj square. This comes by the Cauchy-Squartz inequality. And since this term is just the norm, this can be taken outside. Norm x2 square. And this is again independent of I. So this is summation j from 1 to infinity. Now this is a constant because this is a finite sum as we were given in the problem. So this is some constant times. Let me take it to be c square. Therefore, norm AX L2 norm is less than equal to C times norm X L2 norm for every X in L2. Hence, this A is a bounded linear operator on L2. Next, we will show that this is compact operator. We'll again construct a sequence of finite rank operators and show that it converges to A in operator norm. So we claim that this A is compact. Define for any natural number n, for n in n, define a from L2 to L2 such that anx, this is its ith element, is equal to summation j from 1 to n aijxj for all 1 less than equal to I less than equal to n, and 0 for all for all I greater than n. So this anx is of the form summation j from 1 to n a1jxj, summation j from 1 to n a2jxj, so on up to the nth term, j equals to 1 to n anjxj, and rest of the terms are 0. Clearly, you can check that this is a bounded linear operator, and clearly it's a finite rank operator. This implies an is a finite rank bounded linear operator and hence compact. This implies an is a sequence of compact operators. Now we claim that. Let's mark it as our subclaim that an minus a, this norm is the operator norm, goes to 0 as n tends to infinity. Now, for any x in L2 minus 0, that means x is a non-zero vector in L2, let's see how an minus a at this x looks like. So an an, first term, if we look at the first term, here we had the sum is j from 1 to infinity, and in an we have the sum from 1 to n. So when we will write an minus a. So in fact, instead of an minus a, let me write a minus an, so that we have the positive terms. Yeah. So the first n terms will be cancelled out, and we will be left with the rest of the terms up to the nth component, and after that it is just a, because an is 0. So this is something of the form. So this is summation j from n plus 1 to infinity a1j xj, because the first n terms got cancelled out. Summation j from n plus 1 to infinity a2j xj, and so on up to the nth term, summation j from n plus 1 to infinity anj xj, and after that we have summation j from 1 to infinity an plus 1j xj, and so on. So this implies it's L2 norm a minus an x L2 norm square. This is for first n terms. This is summation I from 1 to n modulus summation j from n plus 1 to infinity aij xj square, and for rest of the terms I from n plus 1 to infinity, this is summation j from 1 to infinity aij xj whole square. Now again we'll be using the Cauchy-Schwarz inequality. by Cauchy-Schwarz. This is less than equal to summation I from 1 to n, summation j from n plus 1 to infinity ai j square, summation j from n plus 1 to infinity xj square, plus summation I from n plus 1 to infinity j from 1 to infinity ai j square, summation j from 1 to infinity xj square by Cauchy-Schwarz inequality. And now this term is less than equal to L2 norm of x square, and clearly it is independent of I. Similarly, this is also independent of I. So I can take this outside. This is less than equal to L2 norm square, and this is summation I from 1 to n, summation j from n plus 1 to infinity aij square, plus summation I from n plus 1 to infinity summation j from 1 to infinity aij square. Now this implies norm a minus an x L2 norm by x L2 norm. This is less than equal to summation I from 1 to n, summation j from n plus 1 to infinity mod aij square, plus summation I from n plus 1 to infinity summation j from 1 to infinity mod aij square whole to the power 1 by 2. Now this happens for every x in L2 minus 0. Since the right hand side is independent of x, we can take supremum on both the sides. So we will get so this implies norm a minus an, which is equal to supremum x belonging to L2 minus 0. And this is less than equal to the right hand side. Now this is less than equal to, I can interchange because I and j are independent. So I can write it as this is equal to summation j from n plus 1 to infinity summation I from 1 to n. In fact, if I can write less than equal to, and this is aij square plus summation, taking this as it is, summation j from 1 to infinity aij square 1 by 2. Now this will go to 0 as n tends to infinity because summation I from 1 to infinity summation j from 1 to infinity aij square. This series is finite. This implies summation I from n plus 1 to infinity summation j from 1 to infinity mod aij square is tail of a convergent series. Tail of a convergent series hence converges to 0. Similarly, summation j from n plus 1 to infinity, summation I from 1 to infinity mod aij square. Again, this is the tail of a convergent series. This will converge to 0. That means an converges to a in the operator in the space of bounded linear operators, and an is a sequence of compact operators converging to a in the space of bounded linear operators. Therefore, a is compact. Hence, an is a sequence of compact operators converging to a in LL2. Therefore, a is compact, because we know that this limit should also be compact. Hence, we are done. I hope this solution is fine. If you have any doubt, you can ask. Please go through the proof once again. And if you find any difficulty, you can ask. So if there is no doubt, we can move forward. This question number 9. Let H be a Hilbert space. Let T belonging to the space of bounded linear functions from H to L1 show that T is compact. Here we will be using this Kerr's lemma, which says that in L1, a sequence is norm convergent if and only if it is weakly convergent. In order to show that, this operator must be compact. Solution. Now let Xn be a bounded sequence in H. Clearly, if we can show that there exists a subsequence x and k such that Ax and k is convergent in L1, we will get will get that T is compact. Now, since Xn is a bounded sequence in H, where H is a Hilbert space, which is reflexive, hence it will have a weakly convergent subsequence. Now, since H is a Hilbert space, implies it is reflexive, and in reflexive space we know that closed unit ball is weakly compact. Uh, any bounded sequence must have weakly convergent subsequence. This implies there exists a subsequence xnk of xn such that xnk converges weakly to some x in H. So this is the sign of weak convergence. Now, since T is a bounded linear operator, so we all know that bounded linear operator maps weakly convergent sequence to weakly convergent. Since T belongs to LH L1, this implies TXNK is weakly convergent in L1. And by Sker's lemma, this implies by Sker's lemma, it states that in L1, weak we have weak convergence if and only if norm convergence. Pascal's lemma, Tx and K is convergent in L1. Hence, by the definition, T is compact operator. Therefore, T is compact. I hope the solution is fine. If you have any doubt, you can ask. Or else let's move to the next question, which is last question for this session. We are left with just 10 more minutes. So this is question number 10. Let H be a separable infinite dimensional Hilbert space. Hilbert space. Let En, and from 1 to infinity, be an orthonormal basis for H. Define T, an operator from H to H, such that Tx is equal to summation k from 1 to infinity inner product x with e2k plus 1 times e2k for every x in H. Show that T belongs to LH, T is not compact, and T square is compact. Clearly, T is linear. You can see that yourself. We'll look at the continuity for any x in H, norm Tx square, sorry, norm Tx square, this is equal to summation k from 1 to infinity mod x e to k plus 1 square. Now this is less than equal to norm x square because by Bessel's inequality, because the sequence E2k plus 1 is also an orthonormal sequence. Therefore, this will be less than equal to norm x square by Bessel's inequality. Therefore, norm Tx is less than equal to norm x, and hence this T belongs to LH. Now, if T is compact, then the image of E2n plus 1. So let's say, now suppose if possible, T is compact. Consider the sequence E2k plus 1. Since norm E2k plus 1, it is an orthonormal basis, so its norm is 1 for every k in n. This implies it is a bounded sequence. Now, since T is compact, therefore E2k plus 1 must have a convergent subsequence. This implies TE2k plus 1 must have convergent subsequence. Now let's see how does this TE2k plus 1 looks like. This is, by definition, this is equal to summation. Yeah, so inner product of E2k plus 1 with any E2n plus 1 for any n not equal to k, this will be 0. And because this is orthonormal and hence orthogonal as well. So the sum would be just the term E2k. E2k, because this inner product E2k plus 1, E2k plus 1, this is equal to norm E2k plus 1 square is equal to 1, and E2k plus 1 with E2n plus 1 is equal to 0 for every n not equal to k. This implies the sequence E2k must have convergent subsequence. So obviously that convergent subsequence will be Cauchy as well, but we can see that norm E2k minus E2n for any n k not equal to n, this is just E2k. So you can write it explicitly. This you will get eventually this is equal to E2k square plus E2n square minus 2 times E2k E2n. So since this is equal to 0 and these two are equal to 1, so this is equal to 2. So this is always greater than epsilon equal to 1 by 2, or any other epsilon. For any small epsilon, this will be greater than epsilon. So that means the sequence, if E2k had a convergent subsequence, it must have been Cauchy as well. But from here we can see that no subsequence of E2k can be Cauchy. Hence, it cannot have convergent subsequence. This implies E2k can never. Okay, so let's write it. Is never Cauchy, or it cannot have. It cannot have any Cauchy subsequence. Implies TE2k plus 1 can never have any convergent subsequence. Implies T is not compact. And clearly you can see that this T square, by the definition of T, how the way T is defined, you can see that T square En, you can check it yourself, T square En will be equal to 0 for every n in n, and hence, and since En is the orthonormal basis for H, we will get T square equal to 0, and by triviality, we know that the 0 operator is compact, therefore T square is compact. I hope this solution is fine with everyone. If you have any doubt, you can ask. We still have 2 minutes left. So I hope this whole course was helpful for you people. You must have learned something. If you learned even small thing, that would be a great thing for us. So this is the last tutorial session of this course. Hopefully we'll do some other course next semester. And yeah, if you are watching this on YouTube, you can always ask any doubt in the comment section, or message me on Teams. Okay, then. Thank you.